Pluto is an intriguing and enigmatic realm that exists beyond Neptune within the Kuiper belt. Although it was once deemed the 10th planet in our solar system, it was reclassified as a dwarf planet in 2006. From the outset, Pluto seemed somewhat awkward. Its orbit intersects with those of other planets, which is unusual for a planet. Nevertheless, this has not diminished fascination with this remarkable celestial object. As we venture beyond Earth in search of life, Pluto emerges as a captivating and potentially valuable subject, typically not regarded as a suitable location for life. Recent findings on its surface and beneath its icy exterior have exceeded our expectations. Stunning images captured by NASA's New Horizons mission in 2015, along with additional observations, are challenging our earlier perceptions of Pluto, showing it to be far more than just a small planet. These discoveries have amazed researchers, as they do not align with previous beliefs. As we delve deeper into Pluto's mysteries, we encounter questions regarding the dimensions of this overlooked world. In comparison to Earth, is Pluto as tiny as 1 to the power of 3, 4, 5, or 6? This inquiry encourages us to contemplate the true nature and size of Pluto in the cosmos. The theory of a subsurface ocean beneath Pluto's frozen crust has gained traction due to the presence of stretching fractures and the lack of significant cavities in certain areas, suggesting more recent geological activity than expected. This concept is not new. It has been discussed since 2006 in scientific literature, speculating about the possible existence of subsurface oceans on various celestial bodies, including Pluto. However, the arrival of NASA's New Horizons mission in 2015 brought new insights and breathtaking images that further supported these theories. When the spacecraft reached Pluto, it provided the first detailed view for scientists of one of the solar system's most puzzling objects, revealing a surface characterized by a network of fissures, ice volcanoes, and a gigantic heart-shaped basin. These findings have led some researchers to propose that even more astonishing phenomena may be concealed beneath the surface. For example, analyses of the images uncovered a frozen basin dubbed Plum, located directly opposite Pluto's largest moon, Charon. While this could be a coincidence, the likelihood is slim. Only 5% of models suggest that when this basin was formed, there might have been a subsurface ocean influencing its shape. Later, nitrogen gas in Pluto's atmosphere cooled and settled into the frozen basin, and the accumulation of additional water and ice created a heavy load that shifted Pluto into its current configuration. The concept of a sea beneath the surface has remained a persistent hypothesis, but images of Pluto's far side have reinforced this theory. Solid evidence has been discovered, including a feature known as chaotic terrain, which consists of intricate cracks and scattered plains. This landscape is observed on the opposite side of Pluto from the basin called Sputnik Planum. Researchers have noted similar features on Mars, Mercury, and Europa, one of Jupiter's moons. At these sites, the impact of an asteroid or comet is believed to have generated seismic waves that converged on the opposite side of the body, causing effects akin to the chaotic terrain seen on Pluto. Alden Denton, a graduate student in planetary geology at Purdue University, simulated how an asteroid collision could send shock waves through the dwarf planet. These simulations demonstrated scientific validity, suggesting that such an impact would only have been feasible if Pluto possessed a subsurface ocean beneath its crust. Oliver White, a planetary scientist at the SETI Institute in California, conducted a geological survey of Pluto but did not take part in the analysis of the chaotic terrain. While the features observed on the far side appear similar to others found in the solar system, the low resolution of the images leaves some uncertainty. Nonetheless, there is a consensus among scientists that Pluto exhibits geological peculiarities, especially a significant number of cracks on its far side, which imply the potential for a hidden ocean and offer clues about its possible origins. Hypotheses regarding Pluto's ocean have long suggested that it was once a frozen sea that thawed under the heat generated by radioactive elements in a rocky core. In this scenario, when the ice melted and refroze in the cold basin, wrinkles developed on the surface akin to the wrinkles that form on an apple left in the freezer. These folds would have occurred due to the compression of ice as it melted and the expansion as it froze, resulting in cracks on the surface. If this theory holds true, images of Pluto should display older wrinkles and more recent cracks. However, The images from the New Horizons mission predominantly showed cracks, suggesting that Pluto's surface may have initially been liquid before eventually freezing. Observations from the New Horizons probe uncovered a massive crack stretching across the near side of Pluto, seemingly extending from the North Pole southward. This feature, referred to as Pluto's crack, does not show a sudden change in the surface but is likely a remnant of the ongoing expansion of the frozen ocean. The presence of water on Pluto is also indicated by observations of water on the near side of the planet, which seems to be infused with organic particles. Although it may seem unlikely on a world like Pluto, laboratory experiments have demonstrated that solar and cosmic radiation can create complex organic compounds, including bases found in RNA and DNA. These discoveries bolster the theory that Pluto could host organic molecules and potentially support life. Furthermore, the probe's observations revealed a reddish band at Pluto's equator, possibly composed of organic material associated with a region experiencing greater solar exposure and warmer temperatures. This finding is significant as it suggests the existence of liquid water and organic compounds on Pluto, two essential components for life. Conversely, some UFO enthusiasts have proposed the presence of artificial structures on Pluto, pointing to anomalies in images of the dwarf planet, such as a smoky trail observed on the surface. Although NASA attributes this anomaly to natural features, some believe it could be evidence of extraterrestrial life on Pluto. Often portrayed as a planet of scientific anomalies, Pluto continues to fascinate astronomers and enthusiasts alike due to its complex nature. One of the most striking features of Pluto is its atmosphere, which, despite its distance from the Sun, is dynamic and ever-changing. Composed mainly of nitrogen, with traces of methane and carbon monoxide, Pluto's atmosphere undergoes seasonal fluctuations, expanding and contracting as it orbits the Sun. This phenomenon is reminiscent of the seasonal cycles observed on Earth, although they occur over a significantly longer time frame, given Pluto's 248-year orbital period. During its closest approach to the Sun, Pluto experiences a rise in temperature, causing nitrogen ice to sublimate into gas, thickening the atmosphere. As it moves farther away, the frigid temperatures cause the atmosphere to freeze back onto the surface, leading to a dramatic drop in atmospheric pressure. This cyclical behavior offers valuable insights into the processes governing icy bodies and may serve as a model for understanding similar phenomena on distant exoplanets. Another remarkable feature of Pluto is its varied surface topography, which displays a patchwork of landscapes that mirror its geological past. Observations from New Horizons uncovered areas characterized by smooth plains, lofty mountains, and profound valleys. The region known as Sputnik Planum is particularly intriguing. It contains extensive nitrogen-rich plains exhibiting polygonal shapes thought to result from convection within an underground ocean. These formations imply ongoing geological processes, suggesting a world that is far from geologically dormant. Pluto's mountains, some reaching elevations of 3,500 meters, are primarily made up of water ice, which behaves like rock under the icy conditions of the dwarf planet. The presence of mountains indicates that Pluto has experienced tectonic activity, possibly fueled by internal heat from radioactive decay or the freezing and thawing of subsurface oceans. This geological activity sharply contrasts with the common perception of a static, barren world and highlights Pluto as a dynamic entity with a rich history. The presence of methane on Pluto's surface is also of considerable significance. Methane ice can generate a variety of colors and features, enhancing Pluto's visual complexity. Researchers speculate that interactions between methane and ultraviolet radiation from the Sun may lead to the formation of complex organic compounds. This raises intriguing possibilities regarding the prebiotic chemistry that might occur on such distant worlds, underscoring Pluto's potential as a focal point for astrobiological research. Furthermore, Pluto's relationship with its moons, particularly Charon, adds another layer of intricacy to its story. Charon is relatively large compared to Pluto, and the two are occasionally referred to as a binary system. The gravitational interaction between the two bodies results in synchronized rotation, meaning Pluto and Charon always show the same side to one another. This unique bond influences their orbital dynamics and may contribute to the geological processes on both bodies. Recent research indicates that Charon may also possess a subsurface ocean, further complicating our understanding of the system. The gravitational force from Pluto could generate enough heat within Charon to maintain liquid water beneath its icy exterior. Such findings would suggest that both Pluto and Charon might share a common history of geological activity and potentially even organic chemistry. The scientific community is consistently enhancing its understanding of Pluto, and future missions may reveal even more insights into this remote world. The ongoing analysis of data from New Horizons has sparked discussions about additional missions to the Kuiper Belt, where other similar objects such as Haumea and Makemake might provide comparative insights. Objects like these, which share characteristics with Pluto, could yield essential information regarding the formation and evolution of the solar system. The implications of understanding Pluto extend beyond its own boundaries. Studying such distant worlds can inform theories about the formation of planetary systems, including our own. By examining the similarities and differences among these celestial bodies, scientists can develop a broader perspective on the processes that govern planetary evolution and development across the cosmos. Pluto's distinctive position, along with its potential for organic molecules, ignites speculation about its capacity to support life. While the extreme conditions on its surface may seem inhospitable, the possibility of subsurface oceans offers a glimmer of hope. Such environments could nurture microbial life similar to extremophiles found on Earth, which thrive in harsh conditions. If life does exist in these hidden seas, it could fundamentally alter our understanding of life beyond Earth. Pluto's image has also evolved over the years. Once regarded as the 10th planet and a symbol of hope for discovering new worlds, its reclassification as a dwarf planet sparked debates within both the scientific community and the public. This change has prompted broader discussions about what defines a planet and how we categorize celestial bodies in our solar system. Pluto's narrative serves as a reminder of the evolving nature of scientific understanding and the necessity of revisiting and refining our definitions as new discoveries emerge. Ultimately, Pluto remains a point of fascination within our solar system, challenging assumptions and inviting ongoing exploration. From its intricate atmospheric features and geological characteristics to its potential for harboring organic molecules and subsurface oceans, Pluto embodies the mysteries that lie just beyond our immediate reach. As researchers continue to study this captivating world, each new revelation brings us closer to comprehending not only Pluto itself, but also fundamental questions about life and the nature of the universe. The journey of exploration guarantees that Pluto will remain a topic of interest for many years to come. Pluto's unique traits have led to captivating scientific inquiries and theories, particularly concerning its formation and evolution. One of the compelling aspects of Pluto is its potential for cryovolcanism, the eruption of materials like water, ammonia, or methane instead of molten rock. The existence of extensive smooth plains and towering mountains suggests that some geological cycles may involve the release of these substances from beneath the surface. The idea of cryovolcanoes challenges traditional views of volcanic activity and broadens our understanding of geological phenomena beyond Earth. Additionally, the identification of various surface features raises questions about Pluto's atmospheric history. Researchers have noted that Pluto's surface is scattered with bright and dark regions, indicating different chemical compositions and geological processes. The bright areas are primarily composed of nitrogen ice, while the darker regions contain complex hydrocarbons that may form through photochemical reactions driven by solar radiation. These discoveries highlight the intricate interplay between sunlight, surface materials, and atmospheric conditions, inviting further exploration of Pluto's atmospheric features. Moreover, studying Pluto's atmosphere has significant implications for understanding planetary atmospheres throughout the solar system. The atmospheric pressure on Pluto, though extremely thin, exhibits variations that could be related to seasonal changes. This behavior may resemble atmospheric phenomena observed on larger bodies like Mars and could provide insights into the climates of exoplanets with similar characteristics. The ongoing research concerning Pluto also emphasizes the importance of interdisciplinary collaboration. By integrating insights from geology, atmospheric science, and astrobiology, scientists are assembling a more comprehensive picture of this distant world. As technology advances and new missions are planned, the potential for uncovering even more of Pluto's secrets remains tantalizing. Each new piece of information has the ability to reshape our understanding of Pluto, as well as the broader context of icy bodies within the solar system and beyond.